Hello everyone, welcome back to Priority Queues, Trees and Heaps Part 2. We'll continue our previous topic from last week. So last week we covered Part 1 and now this week we'll see Part 2. So let's get started. Okay, so here we have a array implementation. So now this is our heap. It has no linked nodes, so it is much easier to work with. Now we'll dequeue an element from here. The highest value is stored in the root node, index 0. So we have array implementation of 0 to 16, total 17 index, and the highest value is stored in the root node, which is 0. So these remarkable properties of the heap allow us to place the elements into an array, and the red numbers on the previous slide correspond to the array indexes. So let's see the example. Okay, first of all, remove element 46. So we'll remove this element 46. Now we need to move the object at the last node to the root node. We need to keep track of the object in the last position of the heap using a heap size variable. So the heap size is 17 here. Now we can access the object in the last node using elements heap size -1 and assign it to elements 0, like this. Next, decrement the heap size. We'll decrement it by 16. It was 17 before and now we decremented it by 16. Now the value at index 16 can't be used anymore. It will be overwritten on the next in queue. Now we need to find the greatest child of node 0 and compare it to 9. But how do we get the greatest child? By using the formulas we noted earlier, this is why an array can be used. So if you remember from our previous part 1 slide, we had some equations where we were able to calculate the what is the greatest child, what is the value of right child, left child, and then according to those we were able to get some values. So here we have left child. How we can find the left child value? We can multiply the parent value by 2 and then add 1. So 2 into 0, if the parent value is 0, we are multiplying it by 2 and then plus 1, which is 1. So 1 is the left child, and then the right child is like this. The right child is 2. So which one is the greatest child? So obviously 2 is the greatest child. So the greatest child is the value. So the value is 39, which is on 1 index. So the greatest child is 39. So 39 is greater than 9, so we will swap. Okay, now if the greatest child of 9 is greater than 9, then swap. Now we will calculate again, and we have 3 and 4, these two. Now which one is the greatest? Now 32 is the greatest child. So now we'll see if 32 is greater than 9, then we'll swap. Alright, now if the greatest child of 9 is greater than 9, then swap. Again we are calculating it, and then we have 9 and 10, these two. Now here the greatest child is 29, and 29 is greater than 9, so it will swap. Okay, so now we'll check if the greatest child of 9 is greater than 9, then it will swap. So here we are checking with this equation. So we'll see 2 into parent plus 1, which is 19, which is the value of left child. Now here 19 is greater than the heap size. So the heap size is 16 and this one is the left child value is 19. So 9 must be a leaf node. So we can stop here. So an NQ is done by placing the new element at elements, which is the heap size, then swapping upwards. When NQing, the parent is always found by using the parent formula, parent equal to child minus 1 divided by 2. So when we talk about swapping values in programming, it's important to understand that the process is not as straightforward as using two simple assignment statements. If we were to attempt swapping values with the following lines, these elements I equal to elements j and elements j equal to elements ji, we would encounter an issue. Excuse me. On the first line, the original value of elements I would be overwritten and lost, leaving both elements I and elements j holding the same value. Clearly, this does not achieve the desired swap. Excuse my voice, I have cold, so it's kind of messy. So to correctly swap the values without losing data, we need an intermediary step. This is where a temporary variable comes into play. The process involves three assignments. First is store the original value of elements I in a temporary variable, which is temp equal to elements I. Then assign the value of elements j to elements I. Then finally assign the stored value from the temporary variable to elements j. Now this ensures that the original values in both positions are safely exchanged without loss of data. While this traditional method is effective, in some cases, advanced techniques or optimizations such as bitwise operations can be employed to further reduce the work required for swapping. However, those methods come with their own trade-offs in readability and performance, depending on the situation. So, in an NQ or a DQ for a heap, we do not really have to use these three assignment swap, although it helped to visualize how the NQ and DQ process worked. We can save the value we are swapping upwards or downwards. So let's look at an NQ. Okay, now here is a tree. We want to NQ 37. So first let's start. So we'll create a new node in the last position like this. So we have created a new node in the last position. We just pretend that 37 is here. We are pretending. Now we'll check if 37 is greater than 24. 24 is the parent. So we pretend to swap. We just copy 24 here. We now pretend 37 has been placed here, and we compare 37 to 28 to see if we should swap again. So 37 is greater than 28, so we do a one assignment swap again. Now here we swapped, so we pretend to swap. Now we're pretending if 37 is here. Now and compare 37 to 39 to see if we should swap again. Now this time we shouldn't swap because 39 is greater than 37, so we should stop. But we have one final assignment, which is we have to include this value here. So we will stop pretending and then we'll just add this. So now this is DQ. So in DQ we'll use the same technique and we'll swap downwards. So here we have a parent-child formula that can also be sped up. We can just write like left child equal to parent and then less than 1 plus 1. So using these functions we can speed up the parent-child formulas that we saw earlier. Now here is a priority queue header file. So we have array.h, template class data type, class priority queue, then public priority queue, constant array data type, and array void in queue. So we have all these in queue, dequeue, empty, and make empty, those functions here on the header file. And then we also have private data, array data type elements, integer heap size, those. And then we are also including the priority queue.cpp. Now there are two constructors in priority queue.header file. The first constructor just initializes an empty heap. So here the first constructor is the here template class data type priority queue, data type priority queue, elements heap size. The second constructor makes a heap out of an initial array. A heap of size n can be made by inqueuing an elements one at a time, but it would take big O log n time even though it n start off such as small. So a faster method can be used to make a heap out of an initial array in theta n time. The heap will be shown as a linked tree because it is easier to visualize how the method works. But in actuality, when we use the method, we use it on the array. Okay, so here forming an initial heap, how we can do that? So we have initial array, not a heap. Look at the tree form, see how the method works. So we'll see the tree form of this version and we'll see how that method works. So this is a tree method, tree form. Drawing it this way, we can easily see that the initial array is not a heap. So we realize that nodes 8 through 16 are subheaps of only one node. So if you look at here, node 8 is 12, node 8 through 16. These are all subheaps, means these are all like leaves, they don't have any child. So we want to heapify starting with the parent of the last leaf node, which is 16. To find the last leaf node, we use heap size minus 1, which is 16. So the heap size is 17. We are subtracting it by 1, which is 16. Then the parent of the last node is 16 minus 1 divided by 2, which is 7. So heapifying works only if the structure is a heap except for possibly the root. This is true for the structure rooted at index 7, so we can use heapify on it. Then we decrement index 7 and use heapify again. This process continues until we heapify at the root. So 34 is already a heap. So one assignment will do it, which is swap. Now here in this position we'll do the swap. Okay, now the root is now 39. So the result is a heap now. So this is the whole process of how we are doing the heapify. How we are initializing the heap. If you will go through the tree and all these steps again, it will be easier for you to understand the whole process again. Okay, now let's take a closer look at the second constructor of our priority queue class. This constructor allows us to initialize the priority queue using an existing array. It's particularly useful for building a heap efficiently from a predefined set of elements. So here we have template. So the constructor uses a template parameter class data type, making it generic and capable of handling various data types. Then constructor definition, where constructor takes a constant reference to an array of data type and initializes two member variables, elements and heap size. Now next, the for loop is used to perform a bottom-up heap constructions starting from the parent of the last element. The heapify method is called iteratively to ensure the heap property is maintained. So the second part of the constructor adjusts the size of the elements array to the nearest power of 2 greater than or equal to its current length. An integer trie power is initialized to 2. Using a loop, the size is doubled unit until it matches or exceeds the current length of elements. If the size is still smaller, the change size method is called to resize the elements array to the computed trie power. So here, as we discussed earlier, this constructor uses a template parameter and initializes the priority queue with an array. It assigns the array to elements and sets heap size to the array's length. And then for the key part of this slide is just to focus on the for loop starting index. Previously, the calculation began from heap size is minus 2 and greater than 1. Here we have clarified the logic by highlighting that this expression is equivalent to heap size minus 1 greater than 1. So this effectively computes the index of the last parent node in a complete binary tree structure. Heap size minus 1 gives the index of the last element. Subtracting 1 adjusts for the 0 based index, and dividing by 2 using a right shift finds the parent of the last node. Here, like I said, index of last node. And then here this one is index of parent of last node. Then this one makes a heap out of the array. Then this two line finds the least power of 2 that is greater than or equal to the array size. Then line 17 and 18 is checking if the array size is not already a power of 2, then it change it to a power of 2, which helps with maintenance. Okay, let's now dive into the in-queue operation of our priority queue class. This function is responsible for adding a new element to the priority queue while maintaining the heap properties. First, we have template declaration. Then we have method parameters. The in-queue method takes a single parameter, new element, which represents the value to be added to the priority queue. Then heap size check. The first thing the function does is check if the heap size is equal to the length of the elements array. If they are equal, this means the array is full and we need to allocate more space. To handle this, the change size method is called doubling the size of the array, where we are using dynamic sizing. The current length of the array is obtained using elements.length. This value is shifted left by 1 bit, effectively doubling it. The new size ensures enough capacity to accommodate additional elements efficiently. So here the image of the crib on this previous slide was a great metaphor. Just as a crib needs to be resized or upgraded as a baby grows, our array also needs to grow to hold new elements. So now let's see the variable initialization here. We begin by initializing an integer I to heap size. This variable represents the current position in the heap where the new element will be placed. Essentially, I starts at the next available position in the heap. So the for loop checks two conditions. First, I must not be 0 because that indicates we have reached the root. Second, the new element must be greater than its parent to maintain the heap properly. So if these conditions hold, we do the following. Like first, calculate the parent index using I minus 1 greater than 1, which divides by 2 to find the parent in the heap structure. Move the parent element down to the current index I. Then update I to the parent index, effectively moving up the tree to find the current position for the new element. After the loop terminates, I holds the position where the new element should be placed. Now here we initialize I with heap size, which represents the index of the new position beyond the last element in the heap. So remember, heap size minus 1 is the index of the current last element. So by starting with heap size, we are setting up to insert the new element at the next available position. So here, so suppose we are adding the value 30 to a max heap. If the last element is at index 4, heap size minus 1, the new element will start at index 5, heap size. The for loop will then check whether 30 is greater than its parent, move it up if necessary, and find its proper position. So we'll also see another example here. Now here, if you look at we have an open space for new element. We are pretending that we placed new element in this position. So new element is passed in from the client. Now we compare new element with the parent value, say 37. If we say 37, so and do a one assignment swap if new element is greater. So we'll do then the current position becomes the parent of the current position. Afterwards, we compare new element with the parent of the new current position. When the loop stops, I is either 0, the root, or new element which we pretend is at the current position I is less than or equal to its parent. This is how we can do this is how this for loop is working. Now here, either way, we found the place to put new element, and then since we include, heap size is increased by 1. Now if you notice that this is an overloaded operator for elements that are objects. Okay, now a DQ operation. Here, like the enqueue, we have template declaration, then return type and parameter. The method returns a boolean value, true if the element is successfully dequeued and false if the priority queue is empty. Now the first step is to check if the heap size is 0. If it is, the queue is empty, and we simply return false to indicate that no element can be dequeued. Then if the queue is not empty, the root element, highest priority element, is stored in a real element rim element by accessing element 0. The heap size is decremented to reflect the removal of an element, and then the last element in the heap located at element's heap size is moved to the root position at element 0. This is a temporary placeholder for rebalancing. Then we have variable initialization, try size, to initialize the current length of the elements array. This variable represents the tentative size of the array after resizing. Then while loop for downscaling. The while loop attempts to scale down try size to the nearest power of 2 as long as the current heap size fits within a quarter of try size, and if try size is greater than 2. So by performing a right shift, we reduce try size by a factor of 4 in each iteration, ensuring that the array doesn't waste unnecessary memory. Then once an appropriate size is determined, we check if try size is smaller than the current length of the array. This ensures that resizing only happens when it's beneficial. So if resizing is necessary, we attempt to change the size of the elements using the elements dot change size wrapped in a try catch block. Then the try block ensures that the resizing operation is attempted safely. The catch block, though empty here, could be expanded to handle exceptions like memory allocation failures. Then finally, the method returns true, indicating that the resize operation was successfully completed. So here is another example for isEmpty function. It is simply just is an essential utility function in the priority queue class. This method allows us to check whether the priority queue contains any elements. So it is just basically checking if the queue is empty or not. So as with other methods in this class, isEmpty is templated with class data type, and then we have method definition, and then it returns the logic. If heap size is 0, it means the priority queue is empty, and then the method returns true, otherwise it returns false. Then we have make empty, which is used to reset the priority queue to an empty state. This operation is particularly useful when we need to reuse the queue or free up its memory. Then again, it starts with template declaration, and then resetting the heap size, resizing the array. Then we have a try catch block. Now why we are resizing it to 2? Because the queue uses minimum memory when empty, while remaining ready ready to accommodate new elements efficiently. This method is a vital utility for maintaining the priority queue's usability and resource efficiency. Here now next we have heapify. First we are using template declaration and then inline definition. The inline keyword suggests that this method is small and may be expanded directly in the calling code to reduce function call overhead, improving performance. Then variable initializations, like left child, right child, largest. Then child calculation. The index of the left child is calculated using the formula, which is equivalent to 2 multiply I plus 1. This is a fast way to compute the left child index in a binary heap represented as an array. So we'll see a example here. In this code, we have a while loop where the loop runs as long as two conditions are true. First is if the left child is less than heap size. This ensures we don't go beyond the bounds of the heap. And then second is not stop. This boolean flag is used to terminate the loop when the heap property has been restored. Now we'll calculate the right child. Within the loop, the right child index is calculated as left child plus 1. This is the adjacent child node of the current element. Now finding the largest child. The largest variable determines which child is larger. So if the right child index equals heap size, it means there's no right child, so largest is set to left child. Otherwise, it compares the values of left child and right child and assigns the larger of the two to largest. Then we'll compare and swap. So if the value at largest is greater than temp, the value of the current element, the largest child's value is moved to the current index I. So I is updated to largest and left child is recalculated for the next iteration. Then if the value at largest is not greater than temp, the stop flag is set to true, indicating the heap property has been restored. Now after the loop ends, temp is assigned to elements I. This places the original value it's in its correct position within the heap. Now in this diagram we're seeing that it is just visually illustrates this process, because initially the value temp 5 at the root is compared with its children, which is 32 and 34. Then the largest child 34 replaces the root, and the process repeats down the heap. This ensures that the largest value in the subtree bubbles up to the root. Okay, now let's discuss an alternative implementation of heaps known as the linked heap. So while most heaps are array-based, linked heaps provide unique benefits in specific scenarios, particularly when managing memory efficiently. Now, when dealing with large elements, sizes, the array-based heap might not be the most memory efficient structure. This is because arrays often require contiguous memory allocation, which can lead to wasted space or memory fragmentation in cases where resizing is frequent. A linked heap addresses this issue by using a dynamic pointer-based structure similar to a binary tree to store elements. It's important to note that linked heaps have the same time complexity as array-based heaps for core operations like big O log n for insertion. Then if you look at here, now in a linked heap, each node must have left and right pointers. These pointers allow us to navigate to the children of a node, which is critical for operations like swapping during the heapify process. Without these pointers, we wouldn't be able to efficiently identify and access child nodes for comparison and swapping. We also need a pointer to the last node in the heap. This pointer is crucial for maintaining the structure of the heap. It allows us to efficiently remove or replace the last element during the dequeue operation, and it ensures that updates to the heap are performed in constant time or big O1. Now for in-queue, each node needs a parent pointer. This pointer is essential for navigating upward in the heap when swapping is required to restore the heap property. Without a parent pointer, moving up the heap would require additional calculations or traversals that will increase the operation's complexity. So the operation requires a big O1 method for determining whether to place the initial node. This is critical for maintaining the heap's efficiency. The initial placement of the new node is typically at the next available position in the heap, which can be quickly determined using a pointer to the last node or a similar tracking mechanism. Well, we'll now see the list through the heap. So when working with a heap, whether implemented as an array or a linked list, the end of the structure plays a critical role. This is where we perform key operations such as inqueuing or dequeuing. So we work with the end of the array, and we can work with the end of a linked list instead. So it doesn't matter. So here, if you look at this illustration, the diagram, so if we think about an array-based heap, in an array-based heap, the last element of the array is always the point of insertion for new elements when inqueuing. Similarly, when dequeuing, this is where the last element is moved to replace the root. And then on the linked list, when using a linked list to represent a heap, we work with the last node for inqueuing or dequeuing, much like in an array-based implementation. This ensures that we maintain the heap structure and manage memory effectively. Now, let's use this diagram to visualize the process and understand how navigating through the heap works. This diagram represents a typical heap structure with nodes labeled for easy reference. Now, the nodes are arranged to satisfy the heap property, where the value at each node is greater or smaller than its children, depending on whether it's a max heap or minimum. The red lines demonstrates a possible traversal path through the heap, such as during a heapify operation. Now the key observations are like the parent-child relationships. Each parent node is connected to its left and right child. For example, node A is connected to B and C. Node B is connected to D and E, and so on. And then the heap is structured level by level, starting from the root A and moving down to the leaf nodes H to O. This structure allows efficient navigation for operations like insertion and deletion. Now let's focus to a concept known as an embedded heap, which introduces some deviations from the traditional heap structure. This slide highlights how cycles can occur in the structure, making it different from a pure heap. So we can say not a true heap or tree. Like in this case, we are no longer working with a pure heap because the structure doesn't meet the fundamental requirements of a tree. A key characteristic of trees is that they are acyclic, meaning they don't contain any loops. However, in this structure, we have cycles, which disqualify it from being a true tree or heap. So even though the structure isn't strictly a heap, we can identify an embedded heap within it. This means there's a portion of the data structure that still adheres to the heap properties. The root might still maintain the highest or lowest value depending on whether it's a max heap or min heap. Then operations like insertion or removal could still focus on maintaining the embedded heap properties. So embedded heaps are useful in scenarios where strict adherence to tree-like structures isn't required, but certain heap-like properties are still valuable. So let's take a look at the pointers that are critical for managing a heap efficiently, particularly when it comes to operations like enqueue or dequeue. Now we need a pointer at the end of the heap called last. This pointer serves a dual purpose. For enqueue, it tells us where to form a new node, ensuring that the heap structure is maintained. For dequeue, it identifies which node needs to be removed, ensuring we can correctly replace the root and maintain the heap's integrity. In addition to the last pointer, we also need a pointer to the last parent. This is important because it tells us which parent to attach a new node to during enqueue. By tracking the last parent, we can ensure that nodes are added in the correct order to maintain the complete binary tree property of the heap. Now let's see an example of adding new nodes. So here we have last and last parent, and then we'll see here we have F. Now we're adding F, so the F will be last. Now it will be added to C just to make a cycle, because the embedded heaps are always cyclic. So if we are adding a new node, and then you have to connect it with the last parent. So in this cyclic embedded heap, you always have a last and a last parent. So you are adding this after last and then connecting it with the last parent. Again, we are adding G after F, and then we are connecting So now the G is the last, and now we are connecting it with C. This is how we can add a new node. So last parent equal to last parent, which is connecting to the next. So if now D is last parent and then we are adding H after last, so now H is last, then it will be connected with D. Now we'll see how we can remove a node. So when we remove a node, we'll have to bring the last pointer back one node. So if the list through the heap is a single linked list, it might not be easy to find the previous node to bring the last pointer back to. So this is how where we'll use doubly linked list. So here, if you see, if you want to remove this node L, which is last, and F is the last parent, so here removing nodes like constant, if the list through the heap is doubly linked, it's easy to find a node to set last to. So using the doubly linked list, we can also bring last parent back one node when we need to. So here we are just doing it. So this is the node structure. We now have 5 pointers in a node. So if you look at here, left, right, parent, back, next, 5 pointers. Okay, so time consideration. So every time we need to add or remove a node, we'll need to set a number of pointers. In the array-based heap, however, we would be copying a couple of elements on the average in queue or DQ, and then for large element sizes, it is still worthy. If an element size is 20 bytes, 50% of the memory in the linked or embedded heap is wasted. If the element size is 1980 bytes, so 1% of the memory in the linked list heap is wasted. So for large element sizes, it is a worthwhile data structure to consider. Okay, now avoiding special cases. We can avoid handling special cases involving the root by using a root header node, which is similar to the header node in the linked list. The actual root node will branch off a single child of the root header. Should the actual root branch from the left or right side of the root header. So here, if you look at this, the root pointer, last pointer, and last parent pointer will start off pointing to the root header. We move the last parent pointer forward after a right child has been attached to its node. Therefore, the actual root should branch off the right side of the root header. So this is how we'll do. Starting it off, we have root, last parent, root header, and last. Now, since a node has been inserted to the right of the last parent node, it is time to move the last parent. So the last parent is moved here. Now we are in a position to insert to the left and right of this node. So if we insert B here, so B is now last, then it is connected with last parent, which is A. And now we added another new element, C. Now C is last, and then it will be connected with last parent A. Now if we move the last parent to B, you see it is already connected. It is already connected with C and A. Okay, here we still need array.h header file since the client will pass an array into the second constructor. So this is the code where we have class priority queue. Then here we use a bool left, which is used to determine which side of the last parent node to insert on, and also when to move the last parent pointer. Now here the first constructor, which is just have last equal to last parent equal to root equal to and root header. Then this is the second constructor. Now this for loop makes the embedded tree, just inserts, and this for loop makes an embedded heap out of the embedded tree. You have to remember that this root points to the root header. Now we'll see how the body of insert node works on the following slides. Okay, so you have this diagram. We have, if you look at line 106, where we will point the last will point to next, which is equal to new PQ node data type. So here it is pointing to next, and then the next is pointing back, so which is equal to last here, like that. Then last is equal to last pointing next. Now, so this is the last. So then we have last pointing left, which is equal to last pointing right equal to last pointing next, which is null. Then we have last pointing parent, which is last parent, this one. So if is left, it is going to point left, the last parent going to point left, which is equal to last. Otherwise it will point right, which is equal to last. And then last parent is equal to last parent pointing next here. Then we have last pointing info, which is equal to info. Left equal to not left. This is how it will work. And this insert node places a new node at the end of the heap. Now here it will reheap upwards using one assignment swaps. Now this one is the DQ. So this we are checking if equal to left. So if it is true, if the next node to be inserted will be the left child of the last parent node, but we are removing a node, so we have to move last parent back. So we'll go through this diagram again for DQ. So if equal to left, if left equal to true, so last parent equal to last parent pointing back, and then last parent pointing right equal to null. Then here we have last equal to last pointing back. Then delete last, which is pointing next, delete. Then last pointing next, which equal to null here, like that. Okay, now we'll toggle left whenever we have to enqueue or dequeue. It was done in the insert node function for enqueue. This current was set to the actual root previously. If the heap isn't empty, the last step of dequeue is to heapify. So this is the heapify code where this line is using for one assignment swaps. Okay, so here this is the one assignment swap. Here largest points to largest child, so move current down to it. Then we have is empty, which is checking is if the is empty or not. So make empty, make empty we move back through the doubly linked list, freeing each last node along the way. When done, we want the last and last parent pointers to point to the root header. This last points to the root header when the loop stops, which means that last parent also points to the root header. Okay, so that is all for today's lecture. So this two parts of this slide, this topic is very big and very broad, so I hope you understand all these topics, and if you don't understand anything, just let me know. And we have finals coming up, and then so we have assignments due. So if you need any help on your assignments or any lecture or for finals, always let me know, give me an email, or we can have an appointment. So if you need any help, so just go through these slides one more time, and if you don't understand anything, just let me know. Thank you.